As a general rule of thumb, for the limits in this class, I'll usually want you to use algebra or direct substitution in order to evaluate that limit. Okay. However, there is an exception. You might see some that have the directions to either use your calculator or find the limit numerically, and all that really means is use your calculator to help you out, kind of like we did when we were working in the slopes and velocities section. Okay. Let's go ahead and open those graphing calculators. Now that we have our calculators open, I want you to go into your y equals and type in the function sine of 7x over 2x. Don't forget to put the parenthesis around that 2x. We want to make sure that we divide by 2x and not just 2. Okay. All right. The next thing I want us to do is actually hit second and then window, and that's going to take us to table set. And I want our table to actually start at 0 since we're going to try and look at the limit as x approaches 0. Okay. And then for this delta table here, if we arrow down, how about we make this 0.0001? Okay. And then the next thing we'll do is we'll just hit second and then graph, which should take us to the table. Okay. And we chose the delta to be small enough here so that it looks like all these say 3.5, but if I arrow over and then down, you can see that, here, let me move down just a little bit. There we go. As I start moving back up this list towards x equals 0, this keeps getting closer and closer and closer and closer to 3.5. Okay. I'm going to have to arrow over this way if I want to keep going up. Okay. All right, so it looks like we're approaching 3.5. Okay. All right, and so now we can fill in our answer. 3.5 or 7/2. Example 6, consider the piecewise function f of x equals x squared plus 1 if x is less than 4, and 3x if x is greater than or equal to 4. And we want to find the limits below. Do note that each piece of this piecewise function is a polynomial, meaning that if they weren't part of a piecewise function, you could just use direct substitution to evaluate any limit involving that polynomial. Okay. But here we can still pretty much do the same thing, but there is one worrisome point. At x equals 4, we might have to be a little bit more careful. And this is just because it's a piecewise function. There could be a break there. Those two functions might not meet up at x equals 4. Okay. So let's just do the first one. At x equals minus 2, well, x equals minus 2 is not 4. So I can just use direct substitution. And let's just see which formula I should be using. Well, x equals minus 2 is less than 4. So we're going to be using the first one. Okay. So this is just equal to minus 2 squared plus 1, which is 5. And then now for part B, we have this limit as x approaches 4. And like I said, this is potentially a problematic point, so we're going to need to be careful. Let's take both our left and right hand limits and see what they are. If we were to take our limit as x approaches 4 from the right of f of x, well, let's think about this. If we were coming from the right of x equals 4, that would mean that we would be on this function right here, 3x. Okay. So this limit that I'm trying to take here is actually the limit as x approaches 4 from the right of just 3x. And this is just a polynomial whose limit could be found using direct substitution. Okay, so 3 times 4, that's 12. And then we can try and take our left-hand limit. Okay. And so if we're coming from the left, that means we're now going to be on x squared plus 1. Okay. And now I can just use direct substitution because this is a polynomial. So that's going to give us 16 plus 1, so that's 17. This puts us on to our last topic, the squeeze theorem, which the name is actually going to make sense here in a second because we're going to see that we're going to have some functions that are kind of squeezed together or sandwiched together. And so here's the inequality that we want, our compound inequality. So we have some function h, which is really sandwiched between f and g. Okay? And it doesn't have to be sandwiched between them everywhere, just on some interval. Okay? Some interval containing x equals c. And if the limit as x approaches c of f of x is L, and the same could be said about g, then we know that this function that's sandwiched here in the middle, its limit must also be L. So the limit as x approaches c of h of x is equal to L. All right, let's try and apply the squeeze theorem here. So sine of 1 over x we know is between minus 1 and 1. Okay, and we could actually take this inequality and multiply by x squared. Okay. And if we do that, note that x squared's greater than or equal to 0. And this is important because if x squared could be less than 0, then it could flip some of these inequality signs, and we don't want that. So we have minus x squared times x squared sine of 1 over x is less than or equal to x squared. And we know that the limit as x approaches 0 of minus x squared can be solved by just direct substitution. This is just 0. And the same thing could be said about the limit as x approaches 0 of x squared. This limit's also just 0. Okay. So since we have x squared sine of 1 over x sandwiched between minus x squared and x squared, and the limit as x approaches 0 of both of those functions is just 0, we know that the limit as x approaches 0 of x squared sine of 1 over x is 0. And this is by the squeeze theorem.